let's recall what we talked about last time. So G is a profinite group. Oh, sorry, maybe before that. So my coefficient is a finite extension of QL, and random integer O, and then uniformizer var pi, and random field F. So F is a finite extension of FL. So I take my G to be a profinite group satisfying the finite condition star. Namely, there are two equivalent conditions. Maybe just write one thing. So it's H1 of G of any M equals is finite for any sort of let's say F G module M. Okay. So we give ourselves a residual representation G of GLN F. Sometimes I write it as sort of GLV. And last time we defined we talked about sort of deformation functor going from the category of complete Noetherian local ring to the sets, sending a local ring AM to all possible continuous, row from G to GL and A, such that rho modulo the maximal ideal is just sort of the same thing as rho bar. The sort of universally lifts the representation rho bar. Okay. So last time we said this is representable. Well, not quite finished the proof, but representable by R rho bar frame with maximal ideal M rho bar framed. Minus one small thing, which is that somehow the tangent space for this R rho bar frame is finite dimensional. So that's something I'm going to compute. Provided that this max, provided knowing that this sort of M rho bar frame over M rho bar frame squared divided by rho pi is finite dimensional. So today I'm going to just talk about this. Let me make a remark that this is the this is a cotangent space of let me rewrite spec of this deformation ring, frame deformation ring at the maximum at the close point. Well, by modern bar pi, maybe sort of more bar pi. So look at the special fiber of the deformation ring, and somehow this maximum ideal square. I mean, just forget about the bar pi here. That's just sort of the tangent space of this deformation ring. So what we're really computing is computing the cotangent space. We're computing the cotangent space of this deformation. It's like in sort of which direction is this sort of cotangent space pointing at. Right. So here's the proposition. There's a. Let me write it this way. So there's a. Or maybe there are canonical isomorphisms going from let's see. So I want to look at this cotangent space. In fact, I want to sort of compute this tangent space. So I take the dual of this. And this is canonically isomorphic. So, or the same thing as you take the frame deformation functor and then apply it to, F epsilon. Oh, I forgot to introduce this F epsilon. Recall it. this is just when I write this, I sort of really mean fx modulo x squared. So epsilon takes so epsilon is the same thing as x, but when I write epsilon, so by definition epsilon squared is 0. If I write fx, it feels like more like polynomial. When I write epsilon, so by definition epsilon squared is 0. Okay. So this is what is this saying? You can think of this as a deforming your roll bar to a sort of make an infinitesimal deformation of your roll bar. Yeah, and moreover, this is isomorphic to the space of all one cocycles of G with values in R-joint group, R-joint represented roll bar. I introduced this last time, I think. So that's for 1. 2 is that when the non-frame deformation is representable, so endomorphism of say Fg of this roll bar is F. So in the proposition we stated earlier, it shows that this is representable. But we didn't give the proof. We'll give the proof a little bit later. Okay. So when this happens, I guess one can show that m roll bar modulo m roll bar square var pi dual is isomorphic to this deformation without the frame. Now this is sorry. Whenever I write canonical isomorphism, I should write 2 bars, which is a habit. So instead of having like space of 1 cycles, I have the first cohomology. Okay. So let's do this. So I will only prove 1. The proof for 2 is essentially similar. Essentially the same thing. I mean, if you just the only difference is somehow here you have here you don't have to frame the deformation. You have to sort of quotient out by something. And when computing this, you have to quotient out by some relation. That's over here you have the one, I guess. Hold on a second. Which one do I want to prove? Actually, so actually I'm going to prove these 2. So I'll prove this, and then prove this. Okay. So proving this for this one is sort of the same thing. And proving this has additional step than this one. So that's even better. Okay, so I proved this first one. So let me call this one 1. That's what I will prove. This is the 2 I will prove. Okay, and the other 2 cases are sort of similar. Right. So let's see. So let's maybe go from here to here and see what this thing gives me. So going for 1, I use the representability. So def of f epsilon, by definition, or by the representability, this is the Hom of in the category of complete Noetherian local ring, local algebra, excuse me, of this R row bar frame mapping to f epsilon, right? And we know that in this category somehow it will preserve the natural sort of map down to f in some sense. And on the other hand, so over here you have some sort of maximal ideal of this one, and pull back is precisely the maximum ideal here. So the maximum ideal inside this sort of deformation ring definitely will map to this epsilon. But epsilon square on this side is 0. So that means on the left-hand side, the maximal ideal squared is mapped to 0 for any homomorphism. So therefore, so any such map will factor through its maximal ideal squared, because maximal squared is mapped to epsilon. And also, of course, the right-hand side is in characteristic L, so I can do mod bar pi here. So this will definitely always factor through these. Okay. And now I'm going to do I want to say that somehow, so inside of here, if you think of some F vector space, there are two things. One is somehow this R mod M. The other one is M mod M squared, basically, in characteristic P. So you can separate this into two parts. And somehow you know that R mod M will definitely map to the F here, and the other side will map to the epsilon. So let me make the claim here. So this, I want to claim that this is the same thing as Hom. So over here, I'm doing as algebra homomorphism. But down here, I just sort of take F vector space map from maximum ideal square mod maximum ideal square bar pi going to F times epsilon. Okay? So if I have a homomorphism from this ring to F epsilon, of course I can restrict to the maximum ideal here, which will map to the well, ideal generated by epsilon, which is sort of just this vector space. And they factor through this, so definitely have a map going this way. Let's do a map going backwards. So if I have, say, I don't know, say call it phi in here. So how F vector space homomorphism or linear map, and can get a phi tilde here. Well, anything in the deformation ring can be written as some number. So A is in F, and M, and X is in M, right? And everything in the ring is just you can change it by a scalar, and therefore just some number plus some element in the maximum ideal, and then you just map it to A plus phi of X, and then this will give the inverse map. So these two are inverse of each other. And in fact, somehow, the reason is that somehow over here, anything in M, if your square is already 0, both in here and here, so somehow the algebra map is just really, you only see somehow the vector space side. That's all. Okay? So that's how, that's just the two equality. So therefore you have proved the one here. Knowing. Okay. Just erase. So let's do the second part. This is probably the more interesting part because we truly relate this sort of deformation problem to the sort of Galois cohomology we're working with. So let's see. Any questions? So let's see. So let's say we get. So let's maybe construct a map. Let's sort of construct a map from this deformation to here first, and in the construction you're going to see that somehow there's an error going backwards. So let's see. So let rho be a representation lifting rho bar. Okay? Now that means that I will send my G to something that lifts rho bar. So I mean naively I want to write rho bar G plus epsilon times something. Right? So right? So because residually it will look like this and epsilon times something. But to make our life, to make our computation a bit better, I rewrite this term because this is an invertible matrix, right? I rewrite this as 1 plus AG for some matrix A, epsilon, rho bar G. Okay, so basically whatever this star is, I write it as AG times rho bar G. Just another way to sort of parameterize this star. Okay, for some AG in the matrix. Okay. Then the question: what condition that this AG should satisfy so that you have a lift? Namely, you want a homomorphism, right? So you better have this. So let's plug in the definition. So I have 1 plus a g epsilon rho bar g times 1 plus a h epsilon rho bar h. That's equal to 1 plus a g h epsilon rho bar gh. Okay, I have that. So let's multiply it out. Just simple-minded, multiply it out. So take 1 here, so I get rho bar g rho bar h, right? If I take ag here in the first place, so I add ag times rho bar g rho bar h epsilon. This, and this. Okay, and then I use the AH part, so that's going to give me. So note that this matrices you can't commute. They're just matrix multiplication. You have to keep the order. Rho G, AH, rho bar H epsilon. And then you have a term which involves AG epsilon, rho bar G, AH epsilon. When you have two epsilons, it goes away because epsilon squared is 0. So that's it. So the right-hand side is relatively easy to write. Just that. So now let's sort of start to cancel things out. Right. So rho bar is itself a homomorphism, so that's okay. So these will cancel. Rho bar G, rho bar H is rho bar GH. Okay, and now after I cancel this, both sides have epsilon, so I somehow cancel epsilon. Right. And these are all in F now. Right, and then I guess I have this rho bar GH on the right. This also has rho bar GH on the right. This doesn't quite. So anyway, so let's multiply the inverse of rho bar GH on the right. So I will get AG plus rho bar G AH. This doesn't have rho bar GH, so I get a rho bar G inverse. It's equal to AGH. Right? I multiply the inverse of rho bar GH, and then get that. And of course, what it is somehow this. So this is a one co-cycle. Well, in Z1 rho bar, G adjoint rho bar. Yeah, it's very simple. So let's erase the top part. Good. So what if another? So actually, this already proves that. I mean, so somehow this already proves that. Although I said I wasn't going to prove it, but anyways, I already kind of proved that this epsilon is isomorphic to Z1 of G adjoint rho bar. Maybe only at this moment I only have a map. Okay, from this deformation to this. But you can go backwards. You see that if you have a cycle that's sort of represented, co-cycle represented by AG, AH, and AGH, and you define your lift in that way, and so I'm just reversing all the sort of implications. I guess you can reverse it, and then that tells you that the lift is a homomorphism, and that is a lift. So really, this is an isomorphism. So the argument here we give is a sort of if and only if argument. So that dealt with the frame deformation. So let's talk about the non-frame deformation. The only difference is that somehow if I give a row such a representation, I would definitely have a co-cycle. But there are but somehow it's possible that rho is equivalent to some rho bar. If and only if somehow your rho G is equal to x, maybe let me write 1 plus epsilon x conjugate your maybe this is rho prime for some x in matrix. So in the sense that when we talk about this unframed deformation, it's possible that rho and rho bar are equivalent, two ellipses. They're equivalent if and only if they are conjugated by some matrices, which is congruent to the identity matrix modulo the maximum ideal, or modulo epsilon. So therefore, I can always write rho bar G as a conjugate of rho G by something, some x in here. Now, if I apply sort of the same argument we have over here, so then I would write sort of rho prime G being equal to let's see, this 1 plus a prime G epsilon times rho bar G, right? So if I use a rho prime to define this functor here, I will send this rho prime to this a prime G. So I need to compare AG and a prime G, right? So how does a prime AG compare to each other? Well, let's write it out. So let's sort of write a rho prime G as using that formula. And what is rho G? Rho G was this a plus AG epsilon rho bar G, and then 1 plus epsilon x inverse. Okay, so let's do the calculation. It's not that bad. First of all, maybe the inverse is a little bit scary, but then it's not that bad if you remember, if you do like, this is 1 minus epsilon x plus epsilon square x square, and then, but then epsilon square is 0, right? So all of these just dies. So the inverse is just really 1 minus epsilon x. See? So let me get a chalk here. So this epsilon is just really minus x here. Okay. Now let's do the calculation. It's not that bad. So let's see. So this is equal to what? So all these factors I can take 1. That's okay. I get rho bar G. Okay, fine. Let's just write. Maybe for later convenience, let's do one more step. Okay. Let's do a small modification. Now I move this rho G to the other side. I move rho bar G to the right hand side. So what I will get is epsilon times rho bar G in. Oh, ouch. Ouch. Fine. This time. Oh yeah, I was right. Sorry. So I can move this rho bar G to the other side. So what's happening is that inside of the x, I somehow end up conjugating my x by rho bar G and rho bar G inverse. So this multiplied to kill each other. Just take a look at it. Okay, I move this to the other side because eventually, I want to write my rho prime G as this form. So my rho bar G is on the right side. So I move this. Just move it over. Okay. Now I multiply these 3 factors. Just as how I did this, so whenever you have sort of 1 plus ax, sort of 1 plus bx, so this is the same thing as 1 plus a plus bx, epsilon. That's the same thing as 1 plus a plus bx of epsilon. You don't need epsilon squared because it's 0. The same thing here, you have 3 factors. But at the end, you just have 1 plus epsilon times x plus ag minus rho bar g, whatever. X rho bar. I'm sorry. X plus this. Dot. Right. So basically, you just have x epsilon x, ag epsilon, and this thingy in here, and then take out epsilon. Now, if I compare this with the top form here, we see that this guy is a prime G. So this means that AG prime and AG are differed by a one boundary. Right? I mean, because this the difference between AG and A prime G is this x minus action on x. So in canonical homology, if two co-cycles are differed by one boundary, I mean, if their difference is like something like gx minus x. So that's what's happening here. So the conclusion is that if my rho and rho prime are differed by a conjugation, then the way I associate the one co-cycle is differed by one co-boundary. That means that I do have a map from depth of rho bar of f epsilon going into H1 of G of adjoint. And as I said, and of course this process can go backwards. You know, if I change my AG into something AG prime by this factor, I can go backwards and somehow I will get somehow the same thing as conjugating my rho G by that matrix. I mean, all these things are sort of equality all the way. So we see that this is really an isomorphism. Somehow the equivalence relation here is correspond on this side to quotienting by one co-boundary. So that proves the theorem, or the proposition. Are there any questions about this? Okay, wonderful. So now let's settle the. So that findings of the tangent space will show that the frame deformation functor is representable. Now we're going to move to talk about the representability of the unframed one under a stronger condition. Okay. So, but before that, I need some sort of input from algebra geometry. I mean, maybe I should say there are two proofs. So now I want to prove the representability of this unframed deformation when the endomorphism ring of rho of fg of rho bar is f. Okay, there are two proofs. One is the classical ones using so-called Schlesinger criteria. So Schlesinger developed a list of four criteria, four conditions for a function to be representable in this category of complete Noetherian local L algebra. Somehow one can just sort of check those conditions. So I leave this as an exercise for you to check out, I guess. Another way is somehow make sense of the quotient I discussed last time. So spuff of our rho bar frame, quotient of by PGL and what to completion. Okay, and because of the time, I will not give a quick. I will not give an introduction to group schemes. You can. So what a group scheme is basically just a group, and it lives over a sort of base scheme, and then all the group operators are just, sort of morphisms of schemes, and multiplications and inverses are all morphisms of schemes, and the action is like G times X is also sort of so we're gonna use some sort of action of a group scheme over X to X. So this is also sort of like a morphism of schemes. If you think it that way, there's not much different, I guess. But so what I want to do is I want to talk about sort of a quotient of a scheme, or a formal scheme in this case, by a formal group. Let's just maybe give you an indication of why sort of such thing can be done. I will not do the formal version. I will just only do the scheme version. I think the formal version is sort of similar. The argument I think you can just modify the argument to make the make the argument into a formal scheme version. And the theorem I'm sort of making this argument is based on SGA3. 7b, theorem 1.4. The original, so this is the version for formal schemes, but I'm making an easier version of this for schemes, I guess. So let's say K is a S is a spec of. I'm going to write K to be with K a local ring. The good thing is you don't have to think about too much about it. Just pretend it's a field. But when we apply it, K will be O, so it's a local ring. It doesn't hurt to think of K as a field. So you can think of it as kind of variety. That's okay. So let G be a flat group scheme over S. So you can think of it kind of a group. If K is a field, this G is just a kind of a group, but it's a higher dimensional group. In my example, when I apply to this, G is going to be something like PGLN over O. So that's the example I'm going to be using. And such that this is a condition I don't quite understand. But anyway, so because it works in my case, so R is free. R is a free B module. Excuse me, RK module. If it's over a field, this is automatic. But I'm a little nervous about sort of flat things being not free. But anyways, it's not finite though. So this is a finite group scheme, and suppose that G acts on an K scheme, call it Y. Let's write a spec of B, and freely. So this is very important. What I mean by this is that I have G cross Y. As I said, I'm going to talk about the action. I have an action, a morphism, such that, of course, it's like, you have G and H. You can act H on this Y and then act G on that. Or you can multiply G and H and then act on Y altogether. So that gives you the same answer. This means that you have a morphism such that, if you have G cross Y, so you can, first of all, do action and then do another action. Or you can do multiplication and then do act. So this diagram commutes, right? Just like how you define action of a group on a set. So now the commutativity of so you get a commutativity diagram of sort of morphism schemes, and also the identity acts trivially. Maybe I'll just write it down. And if you have sort of base with S, and then I embed my S into G using the identity section, and I do action, that's the same thing as not doing anything. And same for the other one. I can do maybe E1 cross E in a sense that, I don't need, sorry, just that. So that's what I mean by action. Freely means that freeness means that if I have G cross S over 1, this over S, if I do the following, if I do act and I do projection, so on the first coordinate I do action, and on the second coordinate I just project to the Y-th coordinate. So this is a closed immersion. Then somehow, let me write this. Then there exists so-called geometric quotient of x by g. Let me write that explicitly over on the other board. More precisely, if I want to, I want to think of it sort of as x over mod g, right? The quotient by g. So this is in terms of schemes. If you sort of consider this sort of contravariant thing, in terms of structure sheaf on this quotient, it should be. Oh, I'm sorry. I used y. My bad. Quotient of y by g. So this will be my x. Apologize. So the reading of regular functions on x is going to be spec of the functions on y that is invariant under g. So when you quotient by g, the functions will just take invariance. But what do I mean by invariant? Because g is not a sort of actual element. It's sort of a scheme. So what I mean by that is that I take all the elements x in B such that, so I have two ways to get a function from B to, so remember that I have g cross y to y. I have two things I can do. I can do act, or I can do projection. So conversely, if I have an element in the ring B, I have two ways to get to an element over here into B tensor with R. Namely, by pulling back via X or pulling back via projection. So the invariant under G is that when you pull back along either one, you get the same thing. And so two more things. Moreover, this is a technical issue. So the image of this map here, it's x times projection. Projection 2 is precisely, it maps this g cross y to y cross y. It maps precisely to a subscheme that sort of lives sort of y cross y over x that has sort of same image in x. And also, I want to say this is closed because that we know there's a so this can be pulled back by a Cartesian diagram from this x cross x. So anything like sort of y cross y over x embedded into y cross y over s can be pulled back from the diagonal embedding of x into x cross x over s. So therefore, because this is a closed, because my x is affine, so this is a closed immersion. So therefore, this is also closed. And also, this y over x is smooth. Oh, it's smooth if my group G is smooth. But of course, when I apply the G will be PGLN, so it's a smooth group. Let's see. So I think I still have to prove this. So basically, let me sort of quickly say what is this. It basically says that if you have a free action that's somehow that allows you to make a quotient. Somehow the freeness is given by this embedding being a closed immersion. Then you can really make the quotient. Then you end up getting a affine scheme. Okay, and later on we're going to show that in the case of a frame deformation ring, this action is free in the sense that this is a closed immersion, and therefore I do have a quotient. So this construction is somehow, I guess, abstract, but somehow it's clean, I guess. Right. So here's a rough idea. Hold on a sec. So in some sense, just think of, don't think too much about sort of the schemes. Just sort of think about sort of a set. Right over here, my G will act on Y, send Y to GY, right? But this quotient, I can take G invariant, but somehow it's not easy to control very well what we're getting. So the idea is that I make a cover of this. I look at I just bring the actual G there. And I want to kind of make a quotient here. But somehow, but my G action, so this is a nice map. Because my G is taken to be flat, and this is something called faithfully flat. In the sense that a lot of time we're going to do, in fact, in some sense I'm going to do a quotient over here, and then take some, and use that quotient to help understand the quotient over here in some sense. I personally feel like it's a little like faithfully flat descent, but not quite the same. But this is how it's done. So G would act on this. The G action over here is a little bit different. I will send an H and Y to HG inverse of GY. Okay, you just change the action just tiny bit. Twist the like if you project to the second factor, it's still sending Y to GY. But on the first factor, it doesn't act trivially. It acts by rate multiplication. At this moment, it doesn't seem to really help. But then, I want to write this space in a slightly different way. I want to write it in a different way in the sense that I want to write, so G goes to G, but then G cross Y, I want to goes to action of Y. So therefore, this goes to HY. So these two are the same. Basically, somehow I'm twisting the parameterization a little bit. When I twist it, you will see that somehow the action is really simple. So let's see that. So therefore, if I do this, the first one being identity, the second one being the action, so this HG inverse times GY is just HY. So now, on the bottom way of parameterizing this, you see that somehow the action fixes Y along and just acting on the G by multiplication on the right. So in some sense, over here, I do know how to, so in this parameterization, it's easy to see how to quotient by G. Because it's just acting on the first coordinate. If I quotient by G, it's kill the first coordinate, I get Y. So I'm going to use this as a help to understand the quotient I want to make on the left-hand side. Okay. So let's write this in a way that's sort of in a more, I guess, in a way that's easier to turn into exact sequences. So I have, let's write, I'm going to write 3 lines here. 1, 2, 3, okay? But I want to start with the bottom one. So I have two maps from G cross, Y. Did I write Y? Okay, good. So there are two things. Either I do act, maybe I do projection first. Doesn't matter. And somehow, this Y would map to the way I define. So this is my spec of BG. Although I don't quite understand the space in the sense that it's just defined to be the it's just defined in such sort of a strange way, I guess. A little strange, not that bad. Maybe let me explain why I want to write things this way. Because now I want to turn things into the rings. So BG going to B, going to proj 2 square action pullback of sort of ring. So G is R, tensor Y is B. Right? So the reason I write it this way is because if I turn into the rings for these schemes, this BG is the equalizer of these two maps. Or alternatively, you can think of it as sort of the difference of the two maps, and this is being left exact. That's the same thing, okay? So that's why I want to write it this way. But now I want to, so this is a picture on the left here. Now I want to throw in this picture on the right, writing it in a similar way as I write here. So I have coming down G cross Y. This is a projection to the second vector. And I take a Cartesian pullback of this picture. So the Cartesian pullback of this it's a little, I think it's relative, for example, projection 2 and projection 2. So you see that basically each time you do a projection, you get an extra factor of G. So you just have that. Right? Let me make the map a little bit more explicit. How to make this map? Okay. Yes. So I have GHY. Map me over here. I map to GY. This maps over here. So note that somehow these hold on a sec. I think I have a typo here somewhere. So this should be HX. So this one of the factor mapping over here is to use H. The other one must use this G or Y. So on the top one, I do this. That's just Y. By the bottom map, so this is sort of the projection one. Over here, I have projection 1, 2, 1, 3, and this is some sort of a new way of acting. And this maps to HG inverse GX. And this maps GY. Oh, this is projection to the second factor. So this maps to GY. So this is basically sort of imitating what I have over there. And then I can modify it slightly. Somehow the map being GHHY. So that this becomes GHY. And then the other one is HG inverse HY. So somehow, as I said, somehow after some modification, I'm not going to write it here. After some modification, some action is complete on the first factor, but not on the second factor. And therefore, the quotient is precisely Y. And now, let me finish writing this thing here. Therefore, I just copy the top board. So I end up getting a diagram like so. where this kernel is precisely R. Okay. I'll finish this after the break. And we will get the ring side. Now I have that's too loud. Okay. We'll get to the ring side. So at the bottom, okay, I can always define something like that, but somehow the point is that I want to know this BG is of I guess right size in sentence. What if it's 0? Or what if it's very bad? So I can somehow a key property I want to prove is that somehow this B, tensor BG of G B is isomorphic to RKB. Namely, well, when you see this, you have upward arrow this way. I guess you can. I think you can just show that you definitely induce a map this way, or rather induced by this projection too. I guess now one of the points is I want to show this. The first diagram is Cartesian. So this is not given to you directly in some sense. So we have to prove this. So this is where we need to use the freeness condition. And also we have to use the condition that the action of G on Y is free. So I'm going to use it now. So the freeness condition. If I turn it into, I guess, rings, it says that somehow it's B tensor KB using at and then projection. It goes to this. So remember that this R over K is a. So another assumption we need is somehow that R is free. It's a free K module. But of course, it's infinite rank. I didn't say it's sort of finite, because PGL and over the very base is sort of algebra. So it's just about this R is like should be some sort of polynomial algebra over K. In any case, so that this is surjective. So then I can find a free, I guess, free K module B of B, such that maybe I'll just be lazy here. If I do this, its image is isomorphic on that one. It's a little ad hoc, I have to say somehow. This doesn't. I don't require to have any sort of ring structure whatsoever. Just a K module. And why do I want this? So once I have this, so let me still write this. So let me just copy the top row over here. Excuse me, the top row from there. Let's see. You have sort of R cross B. And the bottom one, I will. So I do have this map here. And the bottom one, I will write BG tensor with this over K with this. Let's see, I want a tensor on the left. It's better. So I want a tensor B here. So someone upshots that this is, if you've seen descent, usually we take some sort of ring to do the descent. But now I pick some sort of very sort of infinite rank free module, and I do this. I can do this V here, and this map is sort of using the sort of act pullback tensor with projection, and this is sort of the pullback of this map here. And because somehow this composition is isomorphism, you can check that this is an isomorphism. And also this is an isomorphism. And therefore, I infer that this is an isomorphism. So now if I do B tensor BG with B, I can, let me say, I can somehow using this first isomorphism here. I can first of all replace this. I mean, there's a lot. There's some work to check that what I'm writing here is all this sort of diagram sort of commutes in the way you want it to commute. So I can split up this B via that isomorphism into V tensor with BG. And then I can sort of kill this 2. Becomes B. And then again, because of the way how things are done, so this is isomorphic to R tensor with KB. So therefore, I prove that if I define G invariant of Y that way, I get somehow Y over G of Y being isomorphic to G of Y over S. And let's see. And there's also smoothness, but that follows from Fitzgerald flat descent. Just write it down. Let me just write it down over here. The other case is because, so I want to know whether my Y is flat over Y over G, which is my X, right? So for smoothness, I can sort of do this, right? But then this is the same thing as G cross Y. So this is smooth. Oh, if G is smooth, then that implies this is smooth. But basically flat. Descent. I mean, of course, this is sort of free because B is free over BG, so this is flat, and also basically flat. So it's a little. I have to say I don't quite understand this proof. In a sense, it's a little. It doesn't look like a descent. So it's not a descent, it's a quotient. Good. So at least at this moment I'm happy. So now I want to get back to existence of unframed deformation. I feel like I still need some word, sort of some explanation. So let's just do it. So what I want to prove is that when the residual Galois representation has trivial endomorphism, then this deformation function is representable by some ring. It's just representable. Just write it that way. Actually, before doing the theorem, let me give two examples before proving the theorem of when this condition is satisfied. Okay, example and maybe non-example. Okay, and then I'll prove this. So one case is called rho bar is so-called absolutely irreducible. So what it means is that it just means it's irreducible, but sometimes if you want to say something is irreducible, the irreducibility may not happen over the coefficient field F. So when I say absolutely irreducible is that if I embed this if I take this representation with F coefficient, I made it into a FL bar coefficient, algebra closed field coefficient. This is irreducible. Small subtlety of the coefficient field here. So once we're in the algebraic closed field, we're feeling a little bit safer, I guess. So here's a reason. Here's a counterexample maybe. So here's an example of irreducible but not absolutely irreducible. Which is that, for example, if you take rho bar from G to say FL square cross, okay, it's a quadratic extension of FL. This you can embed this FL square into GL2 of FL by just thinking, I guess FL square as a two-dimensional vector space over FL, and this element here by how it acts on the sort of the two-dimensional vector space of FL by taking two bases and you get that. And I say this is, if I have a character like so, and embedded into GL2 FL, so this is irreducible as an FL representation. Because there's no one line that's sort of fixed by all G, because this FL square cross will, so if you have a vector here, will sort of transfer you to all the sort of vectors in FL square. So there's no sort of one-dimensional line inside FL that's fixed. But not, of course. I mean, it looks like a character, but not absolutely irreducible. Because if you do sort of rho bar tensor with FL square already, this will break up into sort of two characters, rho bar direct sum with rho bar. But this decomposition doesn't happen over FL. So it looks like somehow this, I guess this representation composing into GL2 is irreducible, but somehow absolute base 10 becomes irreducible. So I do need an absolute irreducible condition for my theorem to work. This is because if you look at the endomorphism of FL of G, of this rho bar here, although this rho bar is, this rho bar is irreducible, and the endomorphism is I guess it's a field with FL square. So that's not the same sort of, I mean, over here I really need the same ground field F and F here. So that's important. So this endomorphism ring is not, it's a field, but it's not FL. It's an extension of FL. Okay. That's one thing. Secondly, so typical example is absolutely irreducible. Okay, but I guess I want to say that absolutely irreducible would imply that the endomorphism ring of F, G, rho bar equals F. Okay. Secondly, if more generally, if rho bar looks like rho bar 1, rho bar 2, rho bar R, and star here, 0 here, with each rho bar I absolutely irreducible and pairwise different. Okay, and of course I don't want to be direct sums, so I want somehow the stars to be not 0, whatever that means. Somehow the extension is very, I guess I don't want the extension to be trivial, so I break this thing into two parts. So I want these sort of stars to be not 0. I'm writing this in a very vague way, but I hope you get an idea of somehow rho bar doesn't have to be irreducible for that theorem to hold, but somehow you have to be some sort of non-trivial extension of pieces. Okay, let's get back to the proof of the theorem. I think this shouldn't be too difficult. Well, it's just a lot of. Anyways. It's just a lot of wording to kind of explain things. So we have shown that the frame deformation is representable by some complete Noetherian local O algebra. And step 1, I said it somehow. I guess you're convinced that at least explain again in more detail that this sort of this PGL and hat acts on split on this deformation ring. So maybe here's a category. Here's tautological argument on this. Is that for each. Let me explain what this means. So for each A for each object in the complete Noetherian local LO algebra. So what is PGL? So A point of this completion. So that's just basically what I use to conjugate things. So that's just 1 plus the matrices in maximum ideal of A. But then I have to quotient out by the center. Namely, quotient out by the diagonal, sort of scalar matrices. Because when you conjugate your representation, the scalar matrix conjugate doesn't have any sort of effect. So I will conjugate things here, but then the scalar matrix would not do anything for the conjugation. So this will act on this deformation space. In the sense that if you have sort of X, I guess, it will act a representation rho into sort of X rho. Oh well, okay. Just write like that. But somehow, in the sense that I think of the X as a lift over here, an actual matrix, and then conjugate. So this will act on all possible lifts. So all possible lifts of this rho bar. But we know that this is the same thing as Ham in this category of R rho bar frame of A. That's the representability of my deformation ring. Oh, excuse me. This is the A point. Excuse me. The A point of this. So in other words, we have a. If I write what action really means, remember act A. It really means a kind of an action. So by action I mean that if I give an element in the group G cross a representation, I will get another representation. Okay. Now I want to take the so-called universal case. Where I'm a little confused here. Where A equals to hold on a sec. Let's see. Sorry. Okay. So I have this, right? But then I can sort of multiply these, or I can think of this. I really want to think of this as split of R rho bar, the A point of this. That's the same thing as this function applied to that. And then the whole thing will be the same thing as PGLN. A point of this, mapping down to I guess split. I don't know. a point of this. Okay. Now I want to take the universal case, where I want to take A to be just this. Anyway, I don't know. Is that too abstract, or? Is that too abstract? Okay, anyway. Or maybe, yeah, do not hesitate, just go. Take the universal case. So that means I take A to be the structure ring on this one. So I take A to be O. Then the left-hand side has a particular element, namely identity. So this A would somehow, this is just basically, so this is nothing but sort of harm of this ring. By definition, this is a harm of PGL and complete tensor R row bar frame to A. So if you take A to be that ring, so there's an identity on the left-hand side. So that will give me a element on the right-hand side. So that's just something in an element in harm of this PGLN tensor with that decision to do this. Of A, sorry, got it wrong way. Oh, sorry, yes, my bad. Somehow the image of this one is the act map. The act. And sometimes the universal object here, the identity will map to the act map. Or rather, I mean, so yeah. It's just, so basically, I mean, in the sense that if you have, for every A, if you have a map from, basically for every A, if you have a map from this, this PGLN, A point of this, times this SPF R row bar frame, so A point of this thing, going to A point of this thing, then you would definitely have a natural morphism from PGLN hat times SPF row bar frame to that. It's by a unique lemma. Maybe that's a better way to do that. Okay. So maybe in explicit terms, let's maybe go back to the original row bar. We try to explain it a different way. So my row bar is the inverse limit. Remember how we defined this? It was somehow defining this as xij of k modulo some relations. This is over inverse limit over all the open complex subgroups of this one. So it's over H, and then these are, so this ring is called Ri, right? And I can define an action already on the level of Ri's. Let's just say Ri, we call it frame. Going to Ri frame tensor with OPGLN. So that map is going by sending xijk, thinking of it as somehow the ij's entry of the image of this case element in the generator of this Gmod H. So this will be mapped to something like summation of what this thing looks like. This is some sort of, looks like O of Zij, right? So this will be sort of summation of sort of Zi I prime kind of times x I prime j prime k, and then some sort of z j prime j, maybe inverse. I mean, in the sense that somehow elements in here has an inverse, so we'll be somehow writing this matrix of z1, 1, z1, 2, to zn, n, and then take the inverse of that matrix, and then the I prime j entry of that. Let me just maybe notify sort of quotation inverse. So the action map goes like sending this entry to that. It's just like somehow rewriting the action of distinct element entry. Okay, it's a bad decision to talk about this. So that's somehow explaining the action on this one. Step 2, I want to show that PDLN cross, you have two things. You can either act or projection 2. This is a closed immersion. Well, this is because, essentially because for every A in here, the A value point of this map is injective. In the sense that if you have a representation and you're conjugating it by something if the thing you conjugate by is not trivial, then you'll get a different representation. So i.e., what I mean by this is i.e., if you have a G and a rho, it maps to rho and it maps to which one goes first? Action. Okay. I joint rho and rho, right? So what I need to show, what I mean by injective is that if I have, I guess, G rho and G prime rho prime goes to the same thing, then these two are equal, right? Injective, but then we know that the rho is already recorded here. So I may as well just consider G rho and G prime rho. And they go to the same thing over here, namely that, suppose that R joint of G. Let me just write is that okay to write? So R joint G of rho. Conjugating rho by G. Just write G rho G inverse, that's okay. So suppose, what I want to show, so suppose these two go to the same thing, namely G rho G inverse is equal to G prime G prime inverse. Then I want to know that G over G inverse is a scalar matrix. So that's what I want. That's what the injective means. Namely, if I have two elements on the left-hand side, G rho and G prime rho, they map to the same thing on the right-hand side. Let's just say that conjugating rho by G and conjugating rho by G prime are the same, then these two matrices are off by a scalar matrix. Well, maybe I'll just write sort of H to be the G prime inverse, and or maybe just without laws of, here's the best way. So without laws of generality, let's assume that one of them is 0. Let's assume that G prime is 1. Okay. Okay, I can conjugate it so that I'm just discussing a case where G prime is 1, and then now I'm seeing that so my G, because in the 1 plus the matrix, so I'll be having 1 plus epsilon G, maybe for epsilon g in the matrix. Now we're in the situation that 1 plus epsilon g times rho 1 plus epsilon g inverse is equal to rho. And I want to show that epsilon g is sort of a scalar matrix. I feel like this is not that difficult. What you can do is you can first of all mod maximum ideal squared to look at this equality. I mean, mod maximum ideal, you just get rho equals rho. You don't get anything. Now I mod maximum ideal squared. The left-hand side now becomes sort of epsilon g bar. So the left-hand side now becomes rho plus, or maybe just sort of for any x in G, rho x plus epsilon G rho x plus rho x, minus epsilon rho x epsilon G, right? That's equal to rho x. So you have rho x here. And then when I multiply that out, I have a rho x out. And I have epsilon g times rho x, where I take 1 here. Or I have this inverse, when I mod maximum ideal s squared, this is just 1 minus epsilon g. So I have that. So I cancel these two out. So that means my epsilon g commutes with all the rho x's. But on the other hand, the endomorphism ring of my rho bar is trivial. So that means my epsilon g is trivial mod, or it's a scalar, it's a scalar mod this. And then of course I can modify my epsilon g by something in the scalar matrices, so that my epsilon g is now in the maximum ideal square, and then I do mod maximum ideal third, and go on. So therefore, I eventually prove that my G is really just a scalar matrix. So I'm not going to write it. So this is sort of standard argument. So this way, I proved that this action map evaluated on any A point is injective. Now here's a general fact. Okay, so I'm not going to write there. Okay. Now comes a general statement. Is that okay? So if now, I mean, think about it. So I have a morphism of this. Morphism of this sort of, I think of this as functors, but they're all represented by something, right? So we're down into the situation that if I have it's a morphism in this category, such that for every A, the induced map comm of C to A, that's sort of one of them going to comm of B to A, is injective. So I'm thinking of the situation where I guess my B is R rho bar flat tensor with that, and my C is O PGLM. So my B and C are of these two rings. And we've just proved that the A point of SPUF C going to the A point of SPUF B is injective for every A. Then the phi is surjective. So this is true basically for every sort of, I think, affine schemes or affine rings, sort of just rings. It doesn't have to be sort of complete or anything. And also, before doing the proof, let me note that this claim I had over there plus the general statement already implies that this is PGLN hat times SPUF R row bar frame goes to SPUF R row bar frame squared is a closed immersion. And therefore somehow the action of PGLN along this frame deformation ring is a free action. So that we can invoke earlier proposition, I guess, from the algebra geometry. Well, let's come back to the general statement. This is actually very easy. Nonetheless, let me prove this. So, okay, so suppose not, I guess. B from B to C is not surjective. Let's take a universal case. So let's take so B mapped to C, right? So I can take C tensor B with C. Okay? So I mean, if B was surject onto C, so this tensor will just give me just give me C. I mean, if C were a quotient of B, say, for example, B mod I tensor with B mod I over B, it's just B mod I. I'm not doing anything. But if it's not surjective, this is usually not the same thing as C. Okay, I want to take A to be this, and see what kind of things that I can create for the hum from C to A. So let's see, hum from C to A. Let me just write C to anyways. So there are two maps. I can either map A to A tensor with 1, or I can map A to 1 tensor A. I have a choice. So of course, both of these restrict the same thing when it comes to B. So this map, same map. I mean, because if A belongs to B, then of course A tensor 1 is the same thing as 1 tensor A. Right. But we know that earlier that somehow the condition says for every A, this has to be injective map. So that means that the two maps I give here are the same map. So that means that somehow for every element in C, A tensor 1 is the same thing as 1 tensor A. Sounds a little strange, I have to say. Right? So if this were injective, then any A tensor 1 must be the same thing as 1 tensor A. And I think this would just imply that this is the same thing as C. Right. I mean, so basically the two sides are sort of the same thing. The physics says this is the same thing as this, I think. But then I want to say that if this were not surjective, this is much bigger than this one. Or, I guess. So if B to C is not surjective, then you can find I guess, maximum ideal. Well, in this case, there's a maximum ideal, I guess. You don't have to exist one, but there's only one maximum ideal here. In general, you find a maximum ideal such that B mod maximum ideal goes to C mod maximum ideal is not surjective. Right? if you look at sort of quotient, the quotient must be non-zero at some point of the speckle B. But of course, here my B is a local ring, so there's no choice. Well, if I mod maximum ideal, this becomes a field. This is also I guess a F vector space, right? So now, if you think of what happens when you do this tensor, mod maximum ideal, that's the same thing as maximum ideal C. So that's the same thing as this. I mean, tensor with B, C mod and B. But now we're tensoring over a field. We know we know how to tensor two vector spaces over a field. It's never sort of you never get the same vector space unless you're one-dimensional. So this is definitely not the same thing as C mod. So contradiction. I guess even before that, we already kind of see something very, very strange already in here. If C is not the same thing as B, then it's not going to happen. Okay. So step 3. Now, as I said, I can that general statement plus the claim earlier, I get a action which is free. So now I can invoke the quotients. So now I can define R rho bar to be the kernel of R rho framed projection 2 star action star of O, PGL, and hat. Or maybe a small remark is earlier I proved it for the non-formal version. So this is a completed version of the previous theorem. A proposition, but I think the proof kind of goes through the previous one. There's not much different. I mean, earlier I did it for the non-completed version. This is a completed version of the other one. Okay, and also that I know that the quotient is a nice quotient. That's to say that if I do tensor this with the frame deformation tensor with the non-frame one, the same thing as sort of putting down some sort of actual sort of. So this is basically some sort of formal power series ring. Maybe just write Z1 through Zn squared minus 1. It's an n squared minus 1 variable power series ring. So those two things are given to us by the algebraic geometry result. And also, I know that my frame deformation is formally smooth over non-smooth the non-framed one. I forgot why I want this, but I want it also. Oh, this is formally smooth over. So that's because my group PGLN is formally smooth. So abstractly and non-canonically, so the frame one is just a power series ring over the non-framed one with n squared minus 1 variables. Right. So my claim is that somehow this R rho bar represents the functor deformation, unframed deformation. So let's see. So let's give an A. Proof of this. So let's give an A. I'll try to prove this. It's a little awkward to actually do this, but anyways. So let's see. So step 1 is I want to show I need to show that if I do, because the way I define the non-frame deformation is starting from the framed one by quotient out by the actions. So this is sum of R row bar frame of A, mapping to hum of R row bar A, right? I mean, you have a map from R row bar. It's a kernel of this one, so I have a map from R row bar to R row bar frame. So therefore, you have a map from this one back here. So this factors through the quotient, or the quotient by PTL and A. I want to sort of talk about this on the ring level. This is just basically going through the definitions, I guess, but let's do this anyways. So let's take a phi in here. I mean, because I guess the problem is how I define my R row bar in this way. It's not quite. I know if you quotient out, but so I guess I want to say that then I would get a deformation of row bar of A mapping to hum of R row bar of A, right? But then I have to show this. The first one, before that, I need to show the action factors through this, because I define R row bar as a kernel of that. So I have phi in here, and the G in. I mean, this is. I guess this comes from the tautological statement for the quotient, but let's just spell it out. So I want to say that so want to show somehow phi and G acts on phi has the same image. Should have done this one now. That's because, well, let's first explain what I mean by G of phi. Of course, I know how to write it in terms of. Of course, I know how to write it in terms of matrices, but I can also write it in somehow the action map. So I have an act. I can. So X star will take row bar frame to OPTLN tensor with R row bar. And then G is a point of PTLN, so we will map from OPTLN back to A. Oh, okay, so this will map from OPTLN to A. And also I have a phi which goes to R row bar frame. So I can tensor with that with phi. So I get to this, and then I multiply. I get to A. So this is the whole composition is G acted on B. Phi. I'm just unwind all the definitions. So now what is the image of this G phi under this map? Well, I just have to compose this. Right, so now if I compose my row bar mapping to R row bar frame, I can do act star. Let's just copy this down. And then maybe multiply together. So let's just do A. Okay. So that's composition is the image of. So that's. Just a couple minutes to finish this. But on the other hand, if I over here I do proj. If I do projection to the second factor, so I won't see this G in some sense. So this is precisely the image of phi. And the way I define R row bar is somehow the equalizer of these two maps. So therefore, this, I guess, going from here to here, already I have the same thing. and then I compose this. So that means that these two images are the same. Let's see. So I guess I will not finish proof, and maybe just leave you as an exercise to read it from the notes. Roughly speaking, the search so now this will give you a map like so. The search activity follows from that this frame deformation ring is formally smooth over R row bar, and the injectivity injectivity follows from the fiber product property here. So this gives you the injectivity. The formally smoothness gives you the formally smoothness will give you the search activity. So I will just end here.